have with us now Angelika Rück, a researcher from the University of Ulm in Germany. Angelika is a managing director of the confocal multiphoton microscopy core facility in Ulm, Germany. Her research focus is actually to the utilization of fluorescence lifetime imaging to investigate metabolic mapping of NADPH and FAD+, as well as using phosphorescence lifetime imaging for oxygen sensing. And today, Angelika will actually talk to us about metabolic NADH, FAD, FMN-FLIM in bioenergetic alterations and applications. Angelika, welcome. Will you be able to share your slides with us?
So, good evening from Germany, and it's great to be here. And thanks a lot to the organizers, especially to Holly and you. You did a really very nice work. And thanks a lot also to Wolfgang for sponsoring all these things. And it would be, of course, much better to be in the real life in Berkeley. I think it's nice weather. We have a lot of snow here now. But anyhow, it's a great experience, and I'm a little bit nervous that all the technique is running. So besides giving a talk, you have also to be sure that the technique is running. So I hope everything is fine. In my talk, I will speak about new approaches in metabolic NADH, FID, FMN-FLIM. And especially, I would like to focus on new techniques concerning FID and FMN fluorescence lifetime imaging. Now, the metabolic coenzymes which play a role during metabolic FLIM are nicotinamide adenine dinucleotide, we all know. And this nicotinamide adenine dinucleotide, NADH, is excited at 360 nanometer normally. And it's fluorescent when it's in the reduced state. In this state, if unbound, it possesses a low fluorescence quantum yield. If unbound and if protein bound, it possesses a much higher fluorescence quantum yield. Besides NADH, and this I would like to stress and to discuss in more detail during my talk, the flavin group is also very important. The flavins, which consist on flavin adenine dinucleotide, the whole molecule, with two aromatic compounds, the chromophore isoalloxacine and the other aromatic compound adenine. And this FID is fluorescent when it's oxidized. It's fluorescent at 530 nanometer. With a relatively low fluorescence quantum yield. However, inside the flavin group, also the FMN, the flavin mononucleotide, is quite important. It's here inside this green circle, and it just possesses the isoalloxacine as a chromophore. And because of this, the fluorescence quantum yield of FID and FMN is completely different. So also FMN is fluorescing in the oxidized state. However, the quantum yield is about a factor of 10 compared to FID, because this adenine can quench sufficiently the fluorescence of this isoalloxacine. Now, in the role of the metabolic enzymes in energy metabolism, it's very well known now that two main processes are induced to produce energy. And in case of the anaerobic glycolysis process, NADH, and the cell is getting reduced, NADH, which is produced during this process, is free. It's not bound to proteins, and it possesses short fluorescence lifetime. Whereas during oxidative phosphorylation, during the aerobic metabolism, when the cells get oxidized, NADH is bound to proteins and possesses a long fluorescence lifetime. However, as I will discuss also the flavins, the flavin mononucleotide and the flavin adenine dinucleotide plays an important role in this process. But the role, if they are bound or not bound, what's about the lifetime, is much more complex than the NADH story. Also, in complex 4 of the respiratory chain, oxygen plays a role. Oxygen is reduced to water. And by doing phosphorescence lifetime imaging, we can even inspect and we can even see oxygen concentration, which is quite interesting. Besides this respiratory chain reaction, we have a lot of different dehydrogenases where also FID and NADH, all these enzymes play a role, and this also influences the fluorescence lifetime and makes the story much more complicated as believed before. So just briefly to summarize, during it always switches. During glycolysis, NADH is free. It possesses a short fluorescence lifetime around 400 picoseconds. During oxidative phosphorylation, NADH is bound to proteins and possesses a long fluorescence lifetime around 2.5 nanoseconds. Because we always observe a mixture in our cells, after measuring the fluorescence decay, the intensity decay, we are always doing a B exponential fitting procedure to get the short lifetime component and the long lifetime component together with the exponential cofactors with the amplitudes. And from this we can calculate the mean lifetime. Now, I would like to explain a little bit more the story about FID and FMN, because both are also involved in oxidative phosphorylation in the aerobic process. And in contrast to NADH, these enzymes are fluorescing when they are oxidized, first of all. And also in contrast to NADH, free FID possess a relatively long fluorescence lifetime, whereas bound FID possess a very short fluorescence lifetime. This is due to this fluorescence quenching of the folded FID. That's the adenine molecule is quenching the fluorescence of the isoalloxazine ring. This is not valid for the FMN, for the mononucleotide, and for the mononucleotide, it's found that the bound fluorescence lifetime is very long, even up to 6 nanoseconds. Now there is always a question if the bound FID decreases or increases during glycolysis or during oxidative phosphorylation, and what's going on with FMN. And I will show you some results later on. What I would like to discuss in more detail is always a question: is the redox state, energy metabolism, and the fluorescence lifetimes, 3 different, very important measures, do they correlate? So the redox ratio is in principle the ratio of reduced NADH divided by oxidized NAD+. Because NAD+ is not fluorescing. Britton Chance, more than 40 years ago, he defined the so-called optical redox ratio as the ratio of the fluorescence of NADH, the reduced NADH, divided by oxidized FID. Now there is always a question if this redox state, if this redox state, for example, when the cells are getting reduced, correlate with the so-called fluorescence lifetime. Is it always true that if the redox ratio is high, the redox state is reduced, the lifetime is really short? What is correlated, that's people are sure that there is a correlation between the lifetime and the energy metabolism. For example, glycolysis is always correlated to a short fluorescence lifetime of NADH. But is there also a correlation between the redox state and the fluorescence lifetime? Of course, the same is true for the oxidized state. So in principle, the correlation between the fluorescence lifetime and the redox state is only true if the NAD+ pool is stable. And this is in many cases not true. For example, NAD+ can be metabolized in many different reactions. So thus one has to be careful when comparing different cell systems concerning the redox state. And in this case, the lifetime is only an indicator for the cell metabolism. This was also discussed by many other people. Therefore, it is better to use the so-called NADH redox index. And this redox index defines a relative delta tau, a relative delta lifetime between an 0% state, which means fully oxidized state, and 100% state, which means fully reduced conditions. However, this NADH redox index obviously cannot be used in really in vivo systems. It can only be used in ex vivo systems. Only cells can be fully oxidized and fully reduced, but animals or complicated, even maybe also patients, cannot be fully oxidized or reduced to define this relative delta tau. It would be a nice index, but it's not working in the real life. As I mentioned, I want to discuss in more detail the FID and FMN, and later on new algorithms which overcome some problems. So the FID and FMN, of course, play the important roles in these processes in getting energy in bioenergetics. FMN in the respiratory chain reaction is mostly associated to proteins and functions in complex 1 of the respiratory chain, is in the so-called NADH dehydrogenase. So it gets electrons from NADH, the FMN plus, and transfers it to ubiquinone. Now we can think about glycolysis means that the free NADH is increasing. There should be no further reduction of this FMN plus. However, bound FMN possess a long lifetime, and it could be that the lifetime in our FAT channel, FID, FMN channel, is getting longer because of this glycolysis, because of the FMN. This is a very complex situation which depends on the cells and also specific inhibitors of the respiratory chain. What's about FID? FID is functioning in complex 2 of the respiratory chain, besides, of course, other functions in protein complexes like lip, dehydrogenase, and others. But in the respiratory chain, it's first reduced to FIDH. This FIDH is always bound to proteins. Now, when complex 2 is inhibited, the reduction of FID to FIDH2 is inhibited. Thus, this means the bound fraction of FAT should increase. This was, for example, reported during Parkinson's disease by Chakraborty. And in that paper, it follows that during glycolysis, the bound fraction of FAT in complex 2 increases. The opposite is true during oxidative phosphorylation. So, however, what happens with FID? This is always a question because other people observed the opposite. When we ask about the importance of FMN, it's interesting to see that the quantitative flavin content in different mammalian cell lines means that FMN has a very low concentration compared to FID. For example, here in these HeLa cells, FMN has amount 9.6% quantity compared to FID. However, because of this high fluorescence quantum yield of FMN, the fluorescence intensity arising from FMN could be very high. Because of all these difficulties, new algorithms are now determined and explained, and to get a reliable energy metabolism and in vivo system and imaging system. Again, to mention the optical redox ratio. In this definition, it could be also defined vice versa, but in this definition, it means that as more reduced the cell is, the redox ratio is increasing. The NADH metabolic index I already mentioned is a very important measure, and I will show you some examples. It means the relation of unbound NADH divided by bound NADH. This always needs a B exponential fitting procedure. Now, very nicely in 2017, Periasamy and his group, they defined the so-called FLIRR index, the fluorescence lifetime induced redox ratio, which is the ratio between bound NADH divided by bound FID. And he found that as more oxidized a cell is getting, as more oxidative phosphorylation the cells are doing, this FLIRR index is increasing. What makes all these measures are mixed in this defined OMI index, optical metabolic index. It's a quantitative optical metabolic imaging method, which was introduced by Melissa Scala and her group and quite nicely summarized in a very good review I would like to recommend by Rupsadata. You can see here every algorithm, the different algorithms are here explained in a very nice way. And this is a mix between this intensity-based redox ratio and the lifetimes of NADH and FID. I would like to explain in more detail and show you examples of this metabolic index A1 divided by A2. And in a very nice work by Hauke Studier and co-workers, they studied this metabolic index in a non-invasive metabolic melanoma progression. You can see it here in experimental dermatology, which came out in 2017. And what these people found, they measured this index in the skin, where a tumor was growing underneath the skin. And during tumor development, this metabolic index increased by a factor of approximately 10%. And this 10% increase was enough to see the switch in the cell metabolism. So when A1 divided by A2, this index is increasing by a factor of 10, then we can say there was a switch in cell metabolism occurred. This was also observed by Marina Shirmanova and her group. They observed apoptosis induction in HeLa tumors by using cisplatin. And during apoptosis induction, oxidative phosphorylation was increasing, and they observed this by a switch in this ratio of a factor of about approximately 10%. So 10% seems to be enough to see a switch in cell metabolism, which is quite nice. But now I would like to come back to this FLIRR index, the relation of bound NADH and bound FID. Of course, we need to measure simultaneously NADH and FID-FLIM. And here an example by this group by Horst Wallrabe and Massi Periasamy, they measured the following. They induced by doxorubicin, they induced apoptosis by doxorubicin and measured this doxorubicin response. And what they got during doxorubicin-induced apoptosis, an increase in this FLIRR index, which also meant an increase in oxidative phosphorylation. Our own observations were in correlation to this observation. So we did a measurement of simultaneous NADH-FLIM and FID-FLIM in squamous carcinoma cells and in keratinocytes, in Hackard keratinocytes. And what we observed was that the lifetime of FID increased from the cancerous cells to the keratinocytes, and also the lifetime of NADH increased from the cancerous cells to the keratinocytes, which is consistent with an increase of this FLIRR index. Now I would like to show you how we are measuring simultaneously NADH, FID, FMN-FLIM. So we have here a conventional laser scanning microscope, and we excite simultaneously with two laser lines at 780 nanometer and 880 nanometer. So with two photon excitations simultaneously by multiplexing these two lines. And we have a 3-channel TC-SPC system now adapted to our microscope. And by using the appropriate filter combinations, we can simultaneously measure in one channel FLIM of NADH, in the other channel FLIM of FID and FMN, and in the third channel FLIM of another dye or phosphorescence lifetime imaging also of a phosphor to measure oxygen. I will not go into detail into the techniques because Wolfgang explained this very well, and I think I don't have time. Just to show you, we detected NADH FLIM around 432 nanometer and FID FMN-FLIM around 530 nanometer. And by using these two different excitation wavelengths, we are sure that we got a nice spectral separation between NADH and FID FLIM. So how have we done our fitting procedure? Now for NADH, we tested different things, and we always do a 2 exponential fit. And the best fit we get is when we fix our lifetime, our short lifetime and our long lifetime, and just calculate our amplitudes. What have we done with our flavins? Because flavins, we now know the signal consists on bound FID, on free FID, and on bound FMN. So what we are now doing is a 3 exponential fitting procedure, and we tested different fittings. We tested free and fixed fittings, so fixed fittings for the lifetimes, and I will show you later on the results. So we are always doing, and this is important to remain, we are always doing a 3 exponential fitting procedure for FID in FMN channel. What we got here, we got when we calculated the FID FMN channel in our tumor cells versus our HCAD cells with the different fitting procedures. When we did a free fit tau mean, and the amplitudes A1 and A2 were statistically significant, but not A3, which remains to FMN. What is very important, we got for every fitting conditions for the free fit and also for fixed lifetime fits, we always got an increase in the fluorescence lifetime of the normal cells compared to our tumor cells. And this was just statistically significant. And what was also statistically significant was that the relation that the amplitude of our bound FID was decreasing for our normal cells, for our HCAD cells, for every fitting condition. So always the amount of our bound FID was decreasing in the HCAD cells. And what was also very interesting, FMN bound increases in the normal cells, in the HCAD cells compared to the tumor cells. So FAT bound decreased for the HCAD cells, which correlates with increased oxidative phosphorylation, with an increased FLIRR index, and the FMN bound also increased. Now we wanted to know what's about the fluorescence intensity which we observe in our cells, and therefore we calculated these Q values, so the relative fluorescence intensities for FID bound, for FID free, and for the FMN bound. And what we saw that FID bound and FID free, the fluorescence intensity, not the lifetimes, the intensities were not significantly different for our two cells. However, the FMN was statistically significant for the two cells. And also importantly, our fluorescence signal was highest for the FMN in both of the cells. So FMN really plays a main role when seeing the fluorescence intensities, because the fluorescence intensity consists on the lifetime and on the amplitude. So the fluorescence contribution from FMN could be very, very high. Now we calculated, we compared the NADH metabolic index with different FLIRR indices. So in addition to the FLIRR index, which was defined by Amassi Sami, we now define different FLIRR indices, FLIRR1, FLIRR2, and FLIRR3, which means that bound NADH divided by bound FID, or free FID, or bound FMN. And what we found was that the statistically most significant difference between both cells we got with this so-called FLIRR1 index, which remains to the classical FLIRR index defined by Amassi. So when we do the calculation, the bound NADH divided by bound FID, the significance was the most for the difference of the tumor cells and of the HCAD cells. Now have two more slides where we tried to do this also in co-cultures to see if this is also valid in co-cultures. So we co-cultured our tumor cells and our HARCAD cells, and we did our lifetime fittings in masked areas here in the HARCAD in the SCC4 cells, and we can see here the results. In that case, also for the masked areas for the co-cultures, the FLIRR1 index was the most significant to give the most significant difference in the two cell types. And what was also very interesting, tau mean of NADH was significantly different for the two cell types. However, tau mean of FID was not significantly different in the co-cultures, but this FLIRR1 index was significantly statistically different, which is very, very important and corresponds to our results in monocultures. Now I would like to come to my conclusion. I discussed especially the NADH metabolic index, which just relates to the lifetime of NADH, to the short lifetime component and to the long lifetime component. And I introduced new FLIR indices, which relates bound NADH to the different compounds after the 3 exponential fitting procedure in the FID channel. This means bound FID, free FID, and bound FMN. In conclusion, for all our measurements, the FLIRR1 was gave the most significant result. And in summary, I discussed functional imaging with time-resolved luminescence microscopy, especially NADH, FID, FMN-FLIM, to investigate cell metabolism by using various algorithms. I just mentioned simultaneous FLIM. I didn't show any results because the time was not enough, but you know that oxygen consumption can be quite nicely measured simultaneously by simultaneous phosphorescence lifetime imaging. And last, I would like to thank all the people who were involved in these studies. My group, Nelanyo Naskar, he helps me also with the technique here. Then Svetlana Karlinina and Kirsten Rees, and all the other people in my, which I collaborate from the neurology department, from Russia now, Ilya Krychenkov, Sergei Tunik. I have a nice project together with them. Wolfgang Becker, of course, Patrick Schäfer, the group in Munich, and the funding. And I would like to thank you for your attention. And it's a great event, and it's great for me to be here. Thank you very much.
Thank you very much, Angelika.